In this video, we will learn to solve 10 questions. The book is Concepts of Physics, Volume 2. The chapter is Electric Field and Potential, and the writer is Shree H C Verma. Now, question number 1 to 10 and 11 to 20 already we have seen in previous two videos. The same you can find in the description below. Question number 21 is saying that there are two charged particles which are present on a smooth horizontal table, are connected by a string. Length is given as 1 meter. It is asked in the question that what is the tension developed in this string. We know that whenever there are two charged particles having similar charges, there must be repulsive force between these two, and these force is nothing but responsible to develop tension in the string. So let us first calculate the force between these two. That is the amount of tension developed in this string. Coulomb's law formula is F is equal to 1 by 4 pi epsilon naught Q1 Q2 upon R square. Put the value 1 by 4 pi epsilon naught as 9 into 10 raised to 9. Q1 is 2 into 10 raised to minus 8, similar to Q2, so it's whole square upon 1 meter square. After calculating, we will be able to get tension or the repulsive force between these two as 3.6 into 10 raised to minus 6 Newton. In this question, it is said that there are two charged particles which are suspended from a common point by a string of length 50 centimeter. The balls are having some amount of charge given as 2 into 10 raised to minus 7 coulomb. Mass is given 100 gram. And they are held at 5 centimeter. Once they are released, it is not said in the question that they are at equilibrium. The question is, once they are being released, at that point of time we have to calculate many values. Like in A, it is asked find the electric force between these two. B, it is being asked what is the components of resultant force along the direction of the string as well as perpendicular to the string. In C, it is being asked find the tension in the string, and D, acceleration of either of the balls. So either of the ball means there must be some net force acting on either of the ball, or maybe one ball as well as another ball, because they are subjected to have the or follow the third law of motion. So we have to calculate force, and then because of the net force, what is the acceleration? Because mass is given, we can apply the formula force is equal to mass into acceleration. So let us have this 50 centimeter, 5 centimeter distance between these two, and now we are going to show all the forces on one charge which is being placed over there. So you can see blue line, it is the force of repulsion between these two. Then theta will be the angle between the perpendicular or the vertical axis with vertical axis to one of the string. Because of their mass, mg will be vertical downward. Because of their mass, mg will be vertical downward. We are going to have some directions along the string as well as perpendicular to the string. Mg we are going to break into two rectangular components or resolve into two rectangular components as mg cos theta as well as mg sin theta. Similarly, f we are going to have into two rectangular components, f cos theta as well as f sin theta. If you see, the tension developed in the string is nothing but the addition of opposite forces, that is f sin theta and mg cos theta, which is answer of part C. If we are going to calculate the force between these two, we can simply apply Coulomb's law, 9 into 10 raised to 9 Q1 Q2 upon distance, that is 5 centimeter square. B part is saying components of resultant force along the string as well as perpendicular to the string. So along the string will be f sin theta as well as mg cos theta. Perpendicular, it will be f cos theta and mg sin theta. So resultant may be f cos theta minus mg sin theta or mg sin theta minus f cos theta, whichever is the larger in value that we are going to have in order to solve this question. So A part we are going to solve. Before that, just have this particular value. We are going to use this value in coming course of time for many questions. Whenever there is small angle in the sense 0 to 20 I am talking about. I am not talking about in degree, rather in radians. So if 0 to 20 the value is there, sin theta and tan theta, they are approximately equal for small angles. So if we want to calculate from the diagram sine theta, it is 2.5, that is perpendicular upon hypotenuse. So it will be 0.05. If we require in coming questions, the same value we can use for tan theta as well. So once we get the sine theta, we can get cos theta by taking under root 1 minus sine square theta, and it is very much nearer to 1, that is 0.99875. Now A part is there, we will be using the Coulomb's law. Put the value of charges 1 by 4 pi epsilon naught, distance because it is given in centimeters, so we must change into meter, 5 into 10 raised to minus 2 meter. Calculate, it will be 0.144 Newton. So that is the repulsive force between these two charged particles when they are separated at a distance of 5 centimeter. B part, as I said, that tension is nothing but is being balanced by F sine theta as well as mg cos theta. So along the string, the component or the net resultant force is going to be 0. But yes, perpendicular, there is F cos theta as well as mg sine theta. So we will be finding the net one, F cos theta minus mg sine theta. If it comes positive, it means F cos theta is bigger. If negative, then F cos theta is smaller. Here it is coming 0.095 and it is positive, it means F cos theta is bigger than mg sine theta. C is tension. So tension is being balanced by these two forces along the string, that is F sine theta plus mg cos theta. Again, you put the value F 0.11, sine theta 0.05, m 100 gram, so that will be 0.1 kg, g 9.8, cos theta 0.99875. After getting this added, it will be 0.986 Newton. Now D part is left, we have to calculate the acceleration. So acceleration is equal to net force along perpendicular direction, because along the string it is 0. So net force is equal to mass into acceleration. Acceleration is equal to force upon mass, and that force will be taken from B, that is perpendicular to the string, 0.095 upon 0.1 kg, and it is 0.95 per second square. Question number 23 is saying that two identical pith balls are charged by rubbing against each other. Now let me tell you that whenever two particles are being rubbed against each other, one will be having positive, the other one will be having negative charge. The magnitude of charges will be same, because the number of electrons which are going to come out from one body is going to be gained by another body. So the one which is releasing the electrons will be having positive charge, the another one which is gaining the electrons will be having negative charge. So if you see the arrangement, they are being suspended from two different points. The length of string is given as 20 centimeter, and the distance between the point of suspension, it is 5 centimeter. But the moment the charge is developed on these two because of transfer of electrons, they will be coming closer to each other, and now the distance between them is 3 centimeter. So distance is going to decrease because of the force of attraction. So they will be coming closer at 3 centimeter. Now we have to calculate mass of the object as well as how much tension is going to develop in the string. And the charge coming on these particles is already given 2 into 10 raised to minus 8 coulomb. If we see the arrangement of the forces which is being acted upon one of the particles, it will be tension along the string. That tension will be resolved into two rectangular components, T cos theta, T sin theta. Force of attraction will be towards the positive one. I have taken the negative charge towards the positive one. So, and the weight on the body, it will be vertical downward. So F is going to balance T cos theta, T sin theta. T cos theta is going to balance mg. If you want to calculate the theta, it is 20 centimeter is the length. 1 is the perpendicular because the earlier distance was 5 centimeter. Now the charge is at 3 centimeter. So 1 centimeter left side, 1 centimeter right side, that we will be taking perpendicular. And here if we are going to calculate the sine theta, will be approximately equal to tan theta, and it is nothing but 1 by 20, because for small angles it is possible. Now we are going to calculate force between these two by taking the standard formula, Coulomb's law, and it will be coming as 4 into 10 raised to minus 3 Newton. Now, if we apply the situation at which the charge is present at equilibrium, means F sine theta will be, F will be equal to T sine theta, as well as T cos theta will be equal to weight of the body. If we divide T sine theta by T cos theta, we'll be able to get tan theta, T and T gets cancelled, F upon mg. And from here we can calculate m is equal to F upon g tan theta, because one of the question which is being asked is to calculate mass of the object, then tension. Put the value of F as 4 into 10 raised to minus 3, G is 10 approximately we are going to take. We can also take 9.8, but just to have the simple calculation you can also take 10. And tan theta is 1 by 20. So 1 by 20 into 10, 2. 1 by 2, 4 it is going to get multiplied, so it will be 8 into 10 raised to minus 3 kg, or 8 gram will be the mass of the object. How to calculate the tension now? So we have two equations, F is equal to T sine theta, mg is equal to T cos theta, and take this value, put value of F and sine theta in the equation, and you will be able to get the tension which is going to develop in the string, and that will be 8 into 10 raised to minus 2 Newton. In this question, it is saying that two small spheres having mass 20 gram are suspended from a common point by two insulating strings of length 40 centimeter. The distance between these two charges are found to be 4 centimeter. Once again you can estimate. If you want to calculate the angle from the point of suspension with the vertical axis, it is again going to be 1 by 20, because 4 centimeter, half will be 2, and 40 centimeter is given the length of the string. So it will be 2 by 40, it will be 1 by 20. So if we are going to use sine theta, it will be 1 by 20, as well as tan theta also it will be 1 by 20 only, and it will help in order to simplify our calculation. Then we have to find the charge on this sphere. Look here, 40 centimeter, this is 4 centimeter, and mutual repulsive force, we have to calculate the charge. Mutual repulsive force also we will see whether it is given, not given in the question. Okay, so we are going to again have all the components in this particular diagram, or free body diagram also you can make. At an angle theta, again with the tension there will be two components, T cos theta, T sin theta, mg is there, F is there. Using the same procedure for small angles, sin theta approximately will be equal to tan theta, and that is going to be 1 by 20, that we can use in this particular calculation. Similarly, again at equilibrium, horizontal components will be equal to vertical components, and tan theta is equal to F by mg. F is equal to mg tan theta, and F we know already, it is k q square upon r square. So if we take this particular formula, it will be q square is equal to r square upon k mg tan theta. R we know, k we have the value 9 into 10 raised to 9, m value is given 20 gram, g 9.8, tan theta 1 by 20. Put all the values. R is 4 centimeter. So 4 centimeter means 4 into 10 raised to minus 2. Then k is 9 into 10 raised to 9. M is 20 grams, so 20 into 10 raised to minus 3 kg. G is 10, tan theta is 1 by 20. Simplifying again, it will be coming as 16 upon 9 into 10 raised to minus 15, or 1 by 60 upon 9 into 10 raised to minus 16, so that the for minus 16 out of root under, it will be 10 raised to minus 8. And then 160 upon 9, after simplifying it will be 4.2 into 10 raised to minus 8 coulomb. This charge may be positive, may be negative. In question it is not given that both are positive. I have taken in the diagram both are positive, but if we are going to take both negative also, same situation would be followed, because negative charge also will be repelling each other, and at equilibrium tension resolving components and mg and F would be balancing all the forces which are involved there, and particle would be at equilibrium. Question number 25, it is saying that two identical pith balls, each are having charge q. Again here we can take positive as well or negative. uh, Q are suspended from a common point by two strings of equal length. Find the mass of each ball if angle between the string is 2 theta at equilibrium. So 2 theta is the angle. I have divided into 2 with the vertical axis theta and theta. Length of the string is L. If this distance we want to calculate, it is nothing but one of the rectangular component of L. So along vertical direction, L would be having L cos theta, horizontal direction L sin theta. So L sin theta is helping us to find the total value between the charges. That will be 2L sin theta. So if you want to take the distance between charges, we can take 2L sin theta. Now mg will be vertical downward, force will be in horizontal direction, that is repulsive force, because both are having similar amount of charge. Then t cos theta, t sin theta. We have been doing this exercise, so it will be easy for us. F is equal to, we know as per the Coulomb's law, k q square upon r square. Put the value r as 2L sin theta and we will be able to get 1 by 16 pi epsilon naught q square upon L square sin square theta. We have to calculate the mass of the object. In the previous questions we have taken these equations, at equilibrium t sin theta is equal to f, mg is equal to t cos theta, tan theta is equal to f upon mg. So what about m? M is equal to f upon g tan theta. F already we have calculated. Now let us put the value of f as 1 by 16 pi epsilon naught q square upon L square sin square theta upon g tan theta. After simplifying it, again we are going to have this value as the mass of the object as cos theta q square upon 16 pi epsilon naught L square sin square theta into g. Question number 26 is talking about a particle having a charge of 2 into 10 raised to minus 4 coulomb is placed directly below and at a separation of 10 centimeter from a bob of simple pendulum at rest. You can see there's a simple pendulum. How much charge is there? We don't know. We may have to calculate. But the distance between them is given 10 centimeter. The mass of bob is given 100 gram. And we know because of this 100 gram, bob is going to create some tension in the string because bob is being attracted by the earth. Question is, how much charge we should give to the bob in such a way or so that the string becomes loose. See, if you talk about string, we know that it is having some tension and it will be loose if tension becomes 0. So how tension will be 0 or minimized? When the repulsive force between these two charges are going to equate tension developed in the string like this. F is the repulsive force between these two. Mg is the weight on the bob because of the earth. It is vertical downward. If F is going to be balanced by mg, there is no tension in the string and string will get loose. So that we are going to calculate in this particular calculation. Tension is equal to mg. M is 0.1 kg as it is given 100 gram and g is 9.8 meter per second square. So it will be 0.98 Newton. This is the amount of tension being developed in the string. Now this force, if appearing as repulsive force between these two charges, obviously string will get loose. So this force will be equal to 1 by 4 pi epsilon naught or must be equal to 1 by 4 pi epsilon naught Q1 Q2 upon R square. Q1 is equal to mg R square 4 pi epsilon naught upon Q2. Put all the values which are given over there. So mg is 0.98, R is 10 centimeter. Change into meter, it will be 10 raised to minus 2 meter on being square. And then 4 pi epsilon naught is 1 by 9 into 10 raised to 9 and Q2 is 2 into 10 raised to minus 4. On simplifying it, the value will be coming as 5.4 into 10 raised to minus 9 coulomb and it must be positive. If it is negative, it is going to attract the charge vertically below. Then tension will increase and string will further be tightened. It will not be loose. Question number 27 is talking about two charges which are Q and 2Q are present at certain separation on a smooth table. Separation is given as D. Third charge particle C is to be clamped somewhere, but we don't know where it should be clamped. So the question is being asked, where should the third charge, which is present at C, should be clamped in such a way that A and B remain at rest, or we can say A and B, the force experienced on must be equal to 0. So this is the distance between A and B. C is being placed somewhere on the line joining these two charges, having distance x from A and obviously d minus x from B. Now force on the third charge which is being placed in between. If A is going to apply some force on C, B is also going to apply some force on C, that must cancel each other. Then only there will be zero net charge developing over there. So we are going to equate them by k q dash upon x square is equal to k 2 q dash upon d minus x the whole square. Now we are going to have a quadratic equation. Look here, k will get cancelled, and we will be having 1 by x square is equal to 2 upon d minus x square, or 2x square is equal to d minus x the whole square. If you are going to take this term as a square plus b square plus 2ab, we will be getting one quadratic equation. And if you solve this quadratic equation, you will be able to get the value of x in terms of d, and it is root 2 minus 1 into d. Now that is the distance from A. The remaining we can take d minus this value, d minus root 2 minus 1 d from the B or point B. Now we know that if A we are talking that total force on A must be 0, or B we are talking that total force on B must be equal to 0, then force applied by C on A, force applied by B on A must cancel each other. So cancel each other means the addition must be equal to 0. So take the force on A due to B and C. Again same, k q dash upon x square plus k 2q dash upon d square is equal to 0. And if you put the value or take other side, the same terms are going to be cancelled, and then q dash is equal to minus 2q x square upon d square, and we put the value of x from the previous equation, we will be getting the charge on C as minus 6 minus 4 root 2 into q. So minus 6 minus 4 root 2 into q charge, if being placed from A at a distance of root 2 minus 1 into d, the A and B is not going to experience any net force. Now question number 28 is there. Is saying that two identically charged particles are fastened to the two ends of a spring of spring constant 100 Newton per meter and natural length 10 centimeter. Natural length means there is no elongation as well as no contraction in the spring. The spring is kept without any extension as well as compression. So the system rests on a smooth horizontal table, rest. Okay. If the charge on each particle, when we are saying about the smooth horizontal table, it means there is no friction on the table. Okay. If the charge on each particle is 2 into 10 raised to minus 8 coulomb, find the extension in the length of the spring. Again, if both the charges are similar, there will be force of repulsion. And because of this repulsive force, the tension will be developing if there is a string, and the extension would develop if there is a spring. So now in the question it is given that spring is there, and see the spring constant is 100 Newton per meter. How high the spring constant is there? If you want to get it extended by 100, if you want to get it extended by 1 meter, you have to apply a force of 100 Newton. So spring is quite hard. Okay. Now let us calculate the extension developed in the spring. Before that, we have to calculate Coulombic force of repulsion between these two, and that is the force responsible to develop any kind of extension in the spring. Taking the values, we are going to have the force as 36 into 10 raised to minus 5 Newton. And we know that spring force is nothing but minus kx, where k is the spring constant. If we take magnitude only, we can calculate x is equal to 36 into 10 raised to minus 5 upon 100, and it will be 3.6 into 10 raised to minus 6 meter, or 3.6 micrometer. Can you see the extension, how small it is? As I said, the spring is not very soft. The spring constant is 100 Newton per meter. It means you have to apply more force if you want to develop or to extend it for a larger amount. But repulsive force is not as strong as it can create bigger amount of extension in the string. So our assumption is going to justify, because repulsive force between two similar charges here, which are going to develop certain amount of extension in the spring is quite hard. It is not so soft because the spring constant is high, and that is the precise reason the small amount of electrostatic repulsive force is going to develop small extension, that is in micrometer, and it is 3.6 micrometer. Question number 29 is saying that a particle A having a charge of 2 into 10 raised to minus 6 coulomb is held fixed on a horizontal table. The charge is there, 2 into 10 raised to minus 6, fixed on a horizontal table. A second charged particle of mass 80 gram stays in equilibrium on the table at a distance of 10 centimeter from the first charge. The coefficient of friction between the table and the second particle is 0.c. The table is not smooth, it is rough, and the roughness is given as 0.2. That is the coefficient of friction. We know that if these two charges are being placed, there will be certain amount of force of either repulsion or attraction. Both possibilities are there. Attraction also possible, repulsion also possible. But as in the given question, in the part it is saying that the particle, the other one is going to stay at equilibrium. The mass is 80 gram. So even if attraction is there, you know that friction force is self-adjusting in nature. So if it is going to attract towards it, friction will not allow it to go towards it. It will be developed in another direction. Similarly, if there is a repulsive force, because of that charge wants to move away from the other one, the friction would be developing into the opposite direction. But be there it may be, we are going to calculate the force between these two. How much force is going to act? F. mg is the weight of the particle, and friction which is going to be developed as mu into normal reaction, and that is mu into r, and r is equal to mg, so mu mg. Now this mu mg, which is the friction force, is going to balance the force between these two charged particles, maybe attracting, maybe repulsive. If we take the force as 1 by 4 pi epsilon naught q upon r square is equal to mu mg, q is equal to r square mu mg upon q into 4 pi epsilon naught. You put all the values given in the question, and then you will be able to get charge as 8.7 into 10 raised to minus 8 coulomb, may be positive as well as negative. You can see what I said. If charge is going to have the different value, suppose it is positive, the previous one is positive, repulsive force will be away, and then friction will be in a direction opposite, because it is self-adjusting in nature. So their possibility is there. It may be positive 8.7 into 10 raised to minus 8 coulomb, or negative 8.7 into 10 raised to minus 8 coulomb. Now last question of this particular video. A particle A having a charge 2 into 10 raised to minus 6 coulomb and mass 100 gram is placed at the bottom of smooth inclined plane of inclination 30 degree. Here is the inclined plane. A particle A is present here. Some charge is there on the particle, 2 into 10 raised to minus 6 coulomb, and mass is 100 gram. Placed at the bottom of the smooth inclined plane, inclination is given 30 degree. The question is, where should another particle B having same charge and mass be placed on the inclined so that it may remain in equilibrium? So let us consider this is the B placed here. Let us calculate total forces total forces, means force, their components which are going to balance, which are going to be cancelled, each and everything. So first of all, mg will be vertical downward. But what is the action of B on the inclined plane perpendicular to it, its surface, and that will be mg cos 30 degree. Perpendicular to it, there will be normal reaction, and that will be balancing mg cos 30 degree, and along the vertical down it will be mg sin 30. This is the force which is going to take B down if it is coming down the plane. But because both are charged, some electrostatic force will be there, repulsive force will be there, which is going to balance mg sin theta. So R will be mg cos 30, Fe will be mg sin 30. Distance already is given, distance we have to calculate that at what distance they must be placed. That is being asked in the question. This is the distance R is given. So mass of A, mass of B, 100, 0.1 kg. Then charge on A, charge on B is given 2 into 10 raised to minus 6 kg. At equilibrium, up the plane Fe, that is electrostatic force, down the plane mg sin theta must be equal. Now put the value of F, put the value of mg sin 30, we will be able to get R square is equal to this value. After simplifying it, we will be able to get R is equal to 0.73 into 10 raised to minus 1 or 7.3 into 10 raised to minus 2, and hence R square is equal to under root 7.3 into 10 raised to minus 2 or 27 centimeter. So these two charges are placed at a distance of 27 centimeter. The key point of this question is the down the plane mg sin theta is going to balance the force Fe, or the force of repulsion between these two charges, electrostatic force of repulsion between these two charges up the plane, and then we can calculate, we can simplify, we can get the answer. Thanks for the watching.